today, my announcements, besides the 10th anniversary of the Celebration of Mind, which we have been holding in the name of Martin Gardner and his legacy since his passing in 2010, sadly also includes the news of James Randi's passing. He was one of the best friends of Martin Gardner. I shall share this picture here of both of them. If you have any interesting stories or anecdote within the community linked to James Randi, please let us know. Send them to us via our support email, support@g4gfoundation.org. On happier news, it's my great pleasure to announce DRichards, who is an associate professor of computer science at George Mason University. He is also writing a biography on Martin Gardner, and today we have the pleasure to see him talk about algorithmic puzzles and Martin Gardner. And with this, I pass over to you, Dana.
Very good. All right, welcome. I'm speaking about algorithmic puzzles today, and about a decade ago, I helped Martin Gardner with this book, which was a collection of all of his puzzles, really every puzzle that appeared in Scientific American, not the essays, only the puzzles. And he was famous for his puzzle columns, and I reorganized everything in the book. And as part of my reorganization, I created a part called Algorithmic Puzzles and Games. Algorithmic puzzles is not a term he ever used, and in fact, I don't know anybody else who has used it. A guy named Levitin wrote a book called Algorithmic Puzzles. I said, "Oh, where did you get that term?" And he said, "I stole it from you." So who knows? Somebody should tell me that it's an old term. It has to be, but there it is. But the whole idea behind algorithmic puzzles is that in computer science, we create algorithms, but also in computer science, we have a good sense that the algorithm creation process is like solving a puzzle. But the solution is not, find the answer to a Sudoku puzzle. The answer is, how do you solve a Sudoku puzzle? Okay, so if you're only dealing with the how do you do something aspects, then you're in the realm of algorithmic puzzles. Now, this allows us to bring up some computer science topics to organize this talk. And this talk was originally a much longer talk, so but it allows us to organize some of the topics. And so to that end, let me start with, here's a definition, I apologize. Everybody who doesn't know what an algorithm is that it's a recipe, okay? It's famously called a recipe because you have a set sequence of inputs, you have an output, and you have a finite sequence of steps to transform the input into the output. And that's what an algorithm is. The steps, of course, depends on the computational model you're working with. I also want to point out that the word algorithm is not used correctly by almost everybody in the media. So I'm getting tired of hearing about biased algorithms and stuff like that. So in any event, the algorithm is just a recipe. And Knuth, I think, said something tremendous once, and that was, my favorite way of describing computer science is to say that it is the study of algorithms. Okay, another famous computer scientist, Dijkstra, once said, computer science is about computers the same way astronomy is about telescopes. It's really about algorithms and the way to solve problems by a sequence of steps from a set of steps that you're allowed under your computational model. In any event, with that understanding, and perhaps we can go on to my first broad topic, which is loop invariance. Okay, and loop invariance is a big topic in computer science, and it basically says that if you want to understand an iterative procedure, what you need to do is not figure out what is happening in the normal sense that people imagine. What you have to figure out is what is not changing. To understand an iterative procedure, again, is to understand what is not changing. And this coin game is a very interesting example. It says Alice and Bob, of course it's always Alice and Bob, play a game with a row of 50 coins. The coins are all different, different values. And the goal is to be rich, of course. And so Alice can take a coin from either end of this row, and then Bob takes a coin from either end, and then Alice takes a coin from either end, and you continue until all the coins are taken. Now, what I'm not asking is what is the best strategy for Alice and Bob? What I'm asking is a simpler question, is prove Alice can prevent Bob from getting more. Okay, so what strategy could Alice follow so that she at least won't lose? Okay, just to prove the existence of such a strategy. Well, the answer is a loop invariant that Alice wants to maintain. All right, Alice can maintain the invariant that Bob can only choose between two coins numbered with the same parity. In other words, two even coins or two odd coins. For example, if Alice takes coin number 1, Bob only has a choice of 2 and 50. Suppose he takes 2. Well, then she can take 50, and now he's left with 3 and 49. The point is that whatever he takes, he can take another one of the same parity and leave him with the same choice. So he'll always have evens to choose from, or he will always have odds to choose from. Okay, and so therefore, Alice, by her first move, can choose the parity for the entire game as long as she plays along and maintains this invariant. And therefore, by looking ahead, she can count the total value of all the odd coins and all the total value of all the even coins, and she can choose to take all the odds or all the evens, and therefore she can never lose. She may not win, there may be a tie. For example, if all the coins are the same, a tie is the best possible. So that's an example of a loop invariant, because again, it's what doesn't change as you iterate. Here's another example of that. We have two tables, all right, of numbers, and you only have operations of taking two columns and interchanging the columns, or taking two different rows and interchanging the rows. All right, and the question is, can you, by those operations, can you transform this table into this table? Okay, now this is a problem that I've given to some high school students, and they've looked at it, and some of them have struggled, but I've been pleased to see that several of them have caught on to what's invariant. What's invariant here is that if two numbers are in the same row in the initial arrangement, they will be in the same row in any subsequent arrangement. And if two numbers are in the same column in the initial arrangement, they will be in the same column in the subsequent arrangements. The reason is because if you interchange two columns, the columns contents stay the same, and the row contents, of course, stay the same. If you interchange two rows, the same thing holds. So with that, you notice that the invariant is that people stay in the same row with other items that they started with. You just have to notice that 5 and 6 are no longer in the same row any longer, and therefore this is clearly an impossible target. There are other pairs as well that you cannot achieve. But again, the key is not to do something sophisticated, but just to figure out what remains the same. So Top Swap, which is a game that has sort of a underground community of admirers, was invented by John Horton Conway, of course, and the game has a row that's just a permutation of the numbers 1 through n. And you have to do the same thing. You don't have choices here. You have to take the first number and reverse. So if there's a 3, reverse the first 3 items so that 3 now is in the right position, so to speak. And then there's a 4 there, so we reverse the first 4 items so that 4 is in the first position. And then we reverse the first 5 items and so forth. And we keep doing these reversals. Now 4 reverses and becomes in the 4th position, and then 3 reverses, and then 2 and 1 reverse. The question that Conway asked is simply to prove that 1 eventually comes to the first position. Of course, once 1 comes to the first position, everything stops, all right, because 1 won't move from the first position. Now, this was discussed in Gardner's Time Travel in chapter 6. So what is it that's invariant here? Well, actually, when it was first solved, I don't think people used the concept of invariant, not at least so obviously. There's several proofs of this known, but the one I like is one that is given to us by Herbert Wilf. And what he said was, you take your arrangements, like this is from the previous slide, and for each arrangement in time, you create a binary number so that the ith bit where b sub 1 is the low order bit, is a 1 if and only if that is in position. In other words, 3 is not in position, 1 is not, 4, 5, 2, so you get all zeros. Now after this, 3 is in position, so bit 3 is a 1 and all the others are 0 because nobody else is in position. Now in binary, that's a 4. Now this is the high order bit and this is the low order bit. So this is regarded as a binary number. Now when you do the next swap and you move 4 in position, then this is the binary number. 3 is no longer in position, you see. And then you swap, get 5 in position. Now 5 is in position, but everybody else is out of position. When you put 2 in position, you get these 2 bits on, and then when you put 4 in position, you get these 2 bits on, and then you put 3, etc. So the key that Will noticed was that if you regard these as binary numbers, as the process progresses, these numbers increase. These are an increasing sequence of numbers. Now, why are they increasing? Well, it's because the new sequence has to be greater than the previous sequence because everything above the new bit stays the same, and everything, and that bit is changed from a 0 to a 1. And so if it changes from a 0 to a 1, then of course this whole binary number has to be greater than that, regardless of whatever this is. And therefore, this is an increasing binary, a sequence of binary representations of integers. And therefore, we will eventually have to reach a position because you are going to, there's nothing to stop you. You have to reach a position where you reach an odd integer. Notice if an odd integer is actually what we want. That's when this first bit changes to a 1. And so when we reach an odd integer, well, we can only stay with the even integers for so long, and we have to eventually reach an odd integer, and the game will end. All right, so there's no possibility of an infinite loop in this process. All right, so again, the invariant is the increasing nature. That's what's invariant. Every time we increase the representation of that permutation, and it's a very nice proof indeed. Now, another principle from computer science that shows up in puzzles is illustrated by this, which is not so much as a puzzle as some others, but we'll look at it. We are given n binary strings of k bits. You'll notice that I'm sort of in lecture mode here, so I apologize if you want me to go a little slower, but we will have questions, of course, at the end if you think I've gone over something too fast. Now, we're given n binary strings of k bits. So k is 3 here, and n is 7. Further, this set of these n binary strings, no string is repeated, and exactly one possible string is omitted. Since there are 2 to the k possible strings, the number is going to be 2 to the k minus 1. We just want to figure out which one is missing. Okay, that's the question. How can you find out which one is missing? Now, the problem to this is that we are charged for every bit we inspect. So we start off with kn bits, right? We start off with kn bits and we get charged. So we might say, let's ask what this bit is, and we're told it's a 0. Then we might ask what this bit is, and we're told it's a 1. And we ask what this bit is, and we're told it's a 1. We can ask about these bits one at a time, and after asking enough questions, we're prepared to announce we know which bit string is missing. Okay, now there's a slightly persuasive argument that you have to inspect all the bits, because if there's some bit you don't inspect, how do you know that that is not the complement, so to speak, of the missing string? Okay, and therefore you might have to look at all the bits. Well, that's clearly not going to be true, or I wouldn't be asking you this. In fact, you can do much better than kn, and of course k is going to be roughly log n, of course. You can do better than n log n. You can do it in a linear number of probes, where a probe is asking what a bit is. You can do it actually in only looking at 2 n bits. The way we can do that is, this is our previous example, we look at the high order bit, if you like, and we count how many zeros and ones there are. Now, if there are, in this case, 4 zeros, we know that the missing number does not start with a 0, therefore must start with a 1. So we write that down. We know that the first bit is a 1. but we can throw away all the strings that had started with a 0. They are no longer worth inspecting. However, the strings that start with a 1 still have information for us, but we don't care about the first bit anymore. And so we get 1, 1, stripping off the first bit, 1, 1, 0, 1, 1, 0. Now the key here, which makes this an example of recursion, is that we now find ourselves in the same situation of a smaller instance. In other words, for recursion to work, you have to have the same instance, you have to have the same problem for a smaller instance. It can't be a related problem. It has to be the same problem. And therefore, we see that what we have here is a sequence of 2-bit strings where there's exactly 3, because that's 2 to the k minus 1, and exactly one of these is missing. So it's the same problem. Now we only need to find out which is the missing string amongst these 3. And to find that, we again look at the high order bits, because it's a recursive procedure, count them. In this case, we see that there's a 0 in the minority, and therefore the missing string will have a 0 in the second position, and we can throw these away, strip off that 0, and we get only 1. Of course, that's the degenerate case, and the 1 is in the majority, and so 0 is in the minority, you get a 1. So 1, 0, 0 is the missing string, and sure enough, it's not on our list. So the key is, only takes 2n. Why 2n? Well, it's our old friend, the geometric series. There's n plus n over 2 plus n over 4 plus n over 8, ... So the number of bits you inspect is going to only add up to a little less than 2 in bits, no matter how large k is. So k is irrelevant to the runtime of this algorithm. It runs in 2n bits, and I think is a very good example of recursion. Now, the jar drop problem, which is gaining a lot of currency, so I'm almost reluctant to use this because I think a lot of people have heard this problem, but it's such a beautiful example of recursion. And that is, we have identical jars, and we have a very tall ladder. We need to know the highest rung of the ladder from which a drop jar does not break. Okay, since the jars are identical, every jar from level 11 might not break, and every jar from level 12 will break. So the point is, we want to find the highest rung where, or if we want to find the lowest rung from which there is a break, or which is the same as the highest rung from which a jar does not break. But to make this more interesting, of course, is we're going to limit the number of tests. So we're going to say something like, you're only allowed to do 10 drops. Okay? And we're also going to restrict it by not giving you too many jars. If we give you too many jars, you can simply go to every rung and drop a jar. And but if you don't restrict the number of drops, you can just start at the bottom with 1 jar and walk up the ladder until you find it breaks. So to make it a non-trivial problem, we have to restrict both the number of jars and the number of drops. Okay, so what is the highest ladder you can test? So if I give you these 2 numbers, the question at hand is, how high a ladder can you run your procedure on and answer this question? Okay, so there will be some ladders which you won't be able to answer that question. Moving on. Now, HJD will define, this is the only slide with math on it. HJD is the number of rungs from which you can solve the problem. In other words, if you have a ladder of this height, you can solve the problem. You can find the highest rung which doesn't break, or alternatively, 1 below the first rung where it does break. So the problem is, of course, parameterized by J and D, as I've said. So the only difficult problem here is to figure out where to make the first drop. If you think about it, that's what it boils down to. Where do you make the first drop? From which rung? Because everything is a scarce resource here. So if you want to make the first drop, you have to be very careful where to do it. Well, the answer is in red here. You want to make the first drop at this rung. Why? Well, Hj minus 1, D minus 1 is the highest ladder you can solve using 1 less jar, because if the first drop breaks, you have to progress. So you've lost a jar and you've lost a drop. And this by definition is the most you can deal with if you drop it from that height and, excuse me, so it's a +1 here. You go to the next height, next rung up, and you drop it from there. So if it breaks at the next rung above, then you will have this many rungs below, and we know that's enough rungs to finish the problem. On the other hand, if you break it, drop it and it doesn't break, then you will be able to start from that like a sort of a false ground level and work your way up. How far can you work your way up? Well, you still have the same number of jars, but you've used up one of your drops. And so you get this recurrence relation, and you have these boundary conditions. Okay? And so this will allow you to compute HJD for any J and D. Now, some people will notice that this has a remarkable resemblance to the Pascal's triangle, because if we didn't have this +1 here, this would be a definition of Pascal's triangle. Well, actually, you can sort of get that you can sort of cancel out that +1 by noticing that this subtraction actually is a binomial coefficient. But that's not terribly important. What is also interesting, as a result of the Pascal's triangle, a little bit of algebra shows you that as J increases, in other words, J can't be more than the number of drops, but as J goes from 1 up to the number of drops, this height of the ladder keeps increasing to the limit of 2 to the D minus 1, so a very high ladder indeed. And for the standard problem that you normally have told you, which is 2 and 10, it turns out to be 55, which surprises most people, that you can do a 55 rung ladder with only 2 jars and 10 drops. It seems to be much higher, and of course, it's because of this mathematics here. But this is a fun thing to play with. Create this table, this array HJD, and play with it, and you will have, I think, some epiphanies about how recursion works. But the important thing is that it is recursive, because after the first drop, you'll recursively run the same procedure with D minus 1 on either with J minus 1 or with J. So it's definitely recursive. All right, now this is, if anybody read the abstract for this talk, I promised to answer this question. Now this is a question I found in a book. I forget which book. It's either a book of interview questions at Microsoft or interview questions at Google. But regardless, this was an interview question. And you have to ask yourself, why would this be an interview question? And that's really the point, more than the answer, is why is this a good interview question? So the pirates, you have 5 pirates, 10 gold coins, 100 gold coins, I apologize. And the pirates are strictly ordered by seniority. So before we start, there's number 1 pirate, number 2 pirate, up to number 5 pirate. And the pirates are greedy. They definitely want as much money as possible. They are very logical, and they wish to live. Okay, so we have our ground rules here. Now, the rule that pirates use to divide gold apparently is this. The most senior pirate suggests a division. He says, pirate 1 gets this, pirate 2 gets this many, pirate 3 gets this many, and so forth. And after he's announced his division, the pirates vote on it. Now, if at least half vote for it, then that is done and we're finished. On the other hand, if at least half do not vote for it, the senior pirate is killed and we start over with 4 pirates and so forth. Now, the question asked here is, what happens? Now, you might think, well, there's not enough information. Maybe different things could happen. It's not true. With these ground rules up here, we know exactly what is going to happen. Okay? Now, what makes this difficult for some people is they keep, and in fact, if you give this to somebody, I guarantee you they're going to say something like, you know, he gives himself a little bit more than 1/5 or something like that, which is way off. All right? What makes this so difficult to approach and so counterintuitive is that people don't stop and ask, compared to what? In other words, if a pirate is making a vote, he is voting for what's been offered to him compared to what would happen if he didn't take it. So what is offered to him if he didn't take it? Well, it's what the same situation would be with 1 less senior pirate, right? So that's what you were really voting for. You're not voting for whether you like what you've been offered. You're voting for what you will be confronting if this process continues. So therefore, in order to figure out what to do with 5 pirates, you need to know what will happen with 4 pirates. To know what happens with 4 pirates, you need to know what happens with 3 pirates. With 3, 2, and then 1. So with one pirate, it's pretty clear he gives himself all the coins. What about two pirates? Well, if there's two pirates, number two pirate gives himself all the coins, because when he votes, he's going to vote for it. The other person's not going to vote for it. He has at least half the votes. So that's what happens. With two pirates, number one gets nothing. Now we go to three pirates. Now, with three pirates, what should he do? Well, he needs two votes now, but what should he do with his coins? Well, what he should do is give one coin to number one pirate, 0 coins to number two, and 99 coins to himself, because number one will vote for this, because he knows if he doesn't vote for it, he's going to get 0. And he is greedy. He'd prefer 1 coin instead of 0. All right. So now we go up to 4 pirates. At 4 pirates, what do? Well, when you drop down to 3, the only person who is out is number 2. He gets 0. So when you have 4 pirates, number 4 pirate says, how should I get 2 votes? Because he only needs 2 votes. So all he has to do is buy the vote of number 2. So what he does is he gives 0 coins to number 1, 1 coin to number 2, 0 coins to number 3, and he gives 99 to himself. All right, and he'll win the vote. Now, when you go up to 5, what happens, and hopefully you're following along by now, you'll see what happens. All number 5 pirate has to do is give 1 coin to number 1, 0 to number 2, 1 to number 3, 0 to number 4, and 98 to himself. And he will have bought the votes of number 1 and 3, because they know that they will not get anything if it is reduced to 4 pirates. All right, but again, it's an example of recursion, and that's the reason it's on a Google exam. If you can't think recursively, perhaps you shouldn't be working at Google. All right, so this is testing your ability to think recursively. Now the procedure is given to you, but you're reasoning about the procedure. Okay, now that's that. Now, changing gears entirely, for the latter part of this presentation, I want to talk about another computer science topic that is very much related to puzzles, and that's computational complexity. So here we have a puzzle from Sam Lloyd, the greatest American puzzler of all time, and it's called the archery puzzle, and you're shooting arrows and you're collecting numbers where your arrow hits, and you want to see if you can get a total of exactly 100. The more abstract problem is you're given a set of S integers. You want to pick a subset of S, and you're given a target T, and you want to know whether the subset adds up to exactly T. This is slightly different because there's no repetitions up here, but it's close enough. All right, so we have this set of numbers and a target T. Well, what we need is an algorithm to answer the yes-no question. Can you pick a set of integers? Now notice I said yes-no question. Can you pick a set of integers that add up to exactly T? Now this is a problem that computer scientists understand, and it's related to this puzzle. Fair enough. Unfortunately, it's an NP-complete problem. I do not have the luxury of time to tell you what an NP-complete problem is. All I can tell you is that all known algorithms for all NP-complete problems, are exhaustive and have exponential time in some sense. All right, so let's just take being NP-complete as bad news, because you are the same as a lot of other algorithms, and they all share this property of not being able to be solved in a reasonable amount of time. There are thousands of NP-complete problems known, like the Hamiltonian path problem. Well, down here we have another Sam Lloyd puzzle. You have to get from here to here, and you need to pass through all of the villages on your way. All right, that's a Hamiltonian path problem. This is another monkey problem. Monkey has to go from window to window and so forth. And that's also a Hamiltonian path problem, as it turns out. The point I'm trying to make is that Sam Lloyd was ahead of his time. And there's 2 types of puzzles, in my opinion. There are what I call pastimes, and then there are these types of puzzles, which you are asked to solve something by proving the existence of something. All right. Now, those types of problems tend to be NP-complete problems. And that's the beauty of puzzles as they intersect with the field of computer science. the good puzzles out there, not the pastimes, but the good puzzles out there almost always are NP-complete problems. And that is why they are difficult. And now Sam Lloyd and nobody else, of course, knew about NP-completeness. They just had the innate understanding of what makes a problem hard. And it's amazing how often puzzle designers, puzzle creators, stumbled on Hamiltonian path problems. So I'll give you another example. So this is a famous problem where you want to construct a path from A to here, B from this gate to this gate, and C to this gate, and the paths cannot cross each other. So non-crossing paths is an old puzzle, and Sam Lloyd created this incredibly difficult version of the same problem for these gates and these buildings. But regardless of the antiquity of this puzzle, I just happened to have proven that it was an NP-complete problem because I was working on a version of the problem that had to do with wiring on a single layer. And if you're wiring on a single layer, you're given terminals that you need to connect by a wire, and the wires, of course, on a single layer can't cross each other. And so I proved that this was an NP-complete problem, but of course I was inspired by these problems. And there you go. So these NP-complete problems correspond to real problems. At the same time, they were anticipated by puzzle creators. Now, tip over, Think Fun game was proven to be NP-complete. Solitaire chess was proven to be NP-complete, another Think Fun game. And Think Fun, I want to advertise that they have a good sense, just like Sam Lloyd and other puzzle creators. Think Fun has a good track record of finding puzzles that are difficult in this sense. All right. Now, to do solitaire chess, etc., you need to do some other generalizations I'll talk about in a moment. I was tickled by this example. It appeared in the Journal of Business Economics. Now, we all know, again, another Sam Lloyd puzzle. Train shunting problems have been puzzles for a very long time. And you want to figure out how, with a small side shunt, you need to be able to interchange two passing trains and other variations of that same problem. Well, what they showed was it is strongly NP hard. So I was tickled that in the Journal of Business Economics, we found that this is a computationally difficult problem. But of course, it started out life as a puzzle. I want to point out that there are things harder than NP-complete. Rush Hour, a pretty famous game by Think Fun, was a generalization of an older set of puzzles, sometimes called the Dad puzzle and so forth. And Sam Lloyd created one as well, where you're basically doing sequential movements of pieces and you want to arrive at a desired state. But this is actually harder than NP-complete. I don't have the luxury of time again to explain why, but PSPACE-complete shows that the problem is even harder than NP-complete problems and therefore truly intractable in that respect. But the point here is that, again, they anticipated this and went back 100 years ago, 120 years ago, who knows, maybe 150, when the Dad puzzle was created. They didn't know about any of this. They just knew that it was computationally intractable. They have a good innate sense of this. Now, finally, Bob Hearn, who's been helping with this gathering for Gardner Celebration of Mind, has a nice book with his advisor, Domain, and it talks all about the NP-completeness and NP hardness, etc., of games and puzzles. So if you want to know more about this, this is a tremendously readable book. Not trivial, but readable, and I can highly recommend it. Now, and there are other books along that line as well. But what I want to state here is Sudoku boring, or is it too complex? Now, the reason I want to address this is because people are very confused at this point. So let me make sure we're all on the same page. A game like Sudoku can be shown to be NP hard, a sign that it's difficult. But on the other hand, we all know that Sudoku is a boring puzzle. Why is Sudoku boring? Because we've solved it. In other words, we have the algorithm. The reason word problems in a mathematical textbook are not puzzles is because we know the procedure we're not supposed to follow. It's just a matter of using what we've been told to move forward. So Sudoku is in the same sense. Everybody knows the rules for how to do Sudoku. If you don't know those, of course, it's fun to learn them. But once you know the rules for Sudoku, all it is a test of your acuity. Can you see how to apply the rules? So it is a boring thing to do once you learn all the rules, and you're just, again, testing your acuity, which makes it more of a pastime. But on the other hand, if we generalize it from 9 by 9 to n by n, then those generalizations are what are NP hard. So the core issue is the tip of the iceberg of a harder problem. But unfortunately, because it's only 9 by 9, it is a finite constant size problem and therefore not too difficult. All right, so that transition from small constant size instances to larger ones is what some people miss. So for example, when I said chess solitaire is NP complete, I meant when it was generalized, not the original finite 4x4 version, which was interestingly difficult already. So that's where I want to stop.
We want to stop here and open questions for our audience. And we already have our first participant, and I will give you allowance to talk, and you should be able to unmute.
Yeah, hi, Danny. Can you go back to the problem about dividing the coins between the pirates?
Yes.
A little too fast for me in the case where there are only 2 pirates. So if you can show me the rules again, I'm trying to...
The rules, unfortunately, are what you don't think they are. So I have to emphasize, if at least half a vote for it.
Yeah.
So if there's 2 pirates, half, if one votes for it, it'll pass.
Yeah, but...
so if I give myself 100 coins and I give 0 to pirate number 1,
yeah,
I'm going to vote for it. Pirate 1 is going to vote against it, but it still carries the day.
Pirate 1, is Pirate 1 the number 1 guy, or is Pirate 1 the number?
I apologize. Pirate 5 is the highest seniority. Pirate 1 is the lowest seniority.
We only have 2.
If I didn't make that clear, then everything I said sounds backwards to you.
Yeah, exactly. So let's suppose there's only 2 pirates. Okay, we got down. There's only 2 pirates.
Number 1 has the lowest. Number 2 has the highest priority. Number 2 will propose that he takes 100 and gives 0 to number 1.
And why doesn't number 1 just always hate everything, that, no matter what's proposed, because he knows that that the senior pirate is then going to die?
No, because if it goes to 3 pirates.
No, we're not.
No, he's not. Well, for 2 pirates, he might as well leave the room because he's never going to get anything.
The senior pirate with 2 pirates always loses.
No, the senior pirate always wins because he's the one who proposes the suggestion. The senior pirate is going to suggest that he gets everything. The senior pirate will like his own suggestion. He will vote for it. The junior pirate will not vote for it.
Oh, he gets a vote too.
Everybody votes.
Oh, okay. I forgot.
Here, all pirates vote.
Okay, I forgot that the senior pirate. That was the only thing I missed. Thanks.
I have a question of my own, especially with the reordering of pairs. It kind of reminded me of the Chinese rings problem and the Hamming codes in a certain way. Is there a relation of some sort?
I understand what you say. Reordering of pairs.
So when you had the numbers in order and you were swapping them around to be.
Oh, top swap. Yes,
so, exactly.
Okay.
So the order in binary, well, it's ascending. It's not directly related to Hamming codes, but is there a relationship with puzzles like, I don't know, Chinese rings or something like that, where that is
not really, but I left out some other stuff that's known. If you would imagine, to be like Chinese rings, you would have to have a gray code. Okay, mm-hmm. Chinese rings are based on gray codes, and the gray codes step through all 2 to the n possible binary sequences. Well, it's actually known that you will never be able to step through all 2 to the n binary sequences. And in fact, the longest possible sequence you can have is the n plus first Fibonacci number. Okay, And so that's basically 1.618 to the nth power, which is going to be less than 2 to the n.
Mhm.
Okay, so it's not actually possible to step through all possible binary sequences, and therefore it won't generate a gray code, and therefore doesn't seem to be too closely related.
Okay, thank you. And the question from the audience, please, Don Knuth, please.
Yeah, okay. Nobody else going to ask a question. What's your next slide?
My next slide was going to be, I was going to talk about the sort of the historical notion of algorithms. Take it back in time a little bit further. Would you like me to do that?
That's wonderful.
Okay, well, let me do that for you. Okay, so the word algorithm, as a lot of people know, it's not a secret. It comes from the mathematician Algorithmic, who in 830 wrote this famous book on algebra. He didn't invent everything in it. He was stealing a lot of stuff from earlier numbers from the 600s that were known in India, number systems and methods. He did innovate and explain, and the word algebra, of course, comes from these words in the title of the book. But algorithmic, for some reason, was corrupted to be algebra. But the important point here is this, that the algebraic methods explained in the book were used what's called rhetorical algebra or syncopated algebra. Rhetorical algebra is basically where you just use English, so to speak. And syncopated algebra is where you use English mixed up with a few variables here. So when we say algebra was in these books, it's very deceptive. Of course, algebra, as we understand it, came much later. But this was an important step because the algebra was actually algorithms. The algebra was originally understood to be the steps you take to solve a problem. Okay, and that's the key idea. Now later, Liber Abaci was published by Fibonacci, and again, this is fairly well known. It translates as the book of calculation, which has nothing to do with abacus. Okay, in fact, the entire reason for writing this book was to tell the people who used an abacus that if they used symbolic manipulation, that he learned from Algorithmic, if you use sort of a more symbolic approach, more algebraic approach, more so to speak, even if it's not algebra as we understand it, if you use that approach, you can solve problems and you do not need to use an abacus. This book was extremely famous at the time. Schools were set up to use this algebra. The reason is that commerce in the Arab world was way ahead of commerce in Europe at this time. And so Fibonacci wrote this book simply to import what was known and tell everybody in Europe that we can do better than using an abacus to do our commerce. And so he was focused on commercial problems. Of course, he had other problems like the famous rabbits problem. But the point is that he was instrumental in introducing to Europe the notion of an algorithm. All right. Now, the reason it's extremely famous is pretty clear because it was copied. I should point out to people that no extant copy of this book exists. All right. So the only reason we know what's in the book is because everybody copied it and there's a lot of plagiarism going on. Now, the slow acceptance of algorithms is the real story here. The real story is that, and this is a very famous woodcut also, where we have the abacus versus the algorist. You notice the algorist uses symbols to do the calculations, whereas this guy uses counters. And what people don't appreciate is even though Fibonacci explained to everybody the importance of thinking algorithmically and using symbolic manipulation, the problem was that no one trusted it. It's hard to emphasize this, but it took 300 years for this idea to catch on, okay? And this emphasizes the controversy. The idea is that why would I, as a citizen, trust you writing squiggles on a piece of paper when I can look at you actually moving counters back and forth? I can watch this and understand it. I do not understand what you mean when you write squiggles on a piece of paper. And it took 300 years for people to believe that this was a superior system. Okay, so it surprises people, I think, to know that it was not accepted, even though it was clearly a superior idea. And the idea that after this that algorithms of symbolic manipulation dominated math for centuries. Okay, so slowly after about 1500, people came to understand that math could be best done through the notion of symbol manipulation. Unfortunately, it wasn't until Boole and Frege that symbolic logic arose. Only when this happened did math come to maturity. Only when we understood that most math, together with logic itself, can be done through symbolic manipulation, did math come to fruition, in my opinion. What's more interesting, I think, is everybody knows about Alan Turing, but Alan Turing's contribution was that he realized that all computing is nothing more than symbol manipulation. Computing has nothing to do with numbers. Now, he wasn't the first to discover the big theorem that's associated with them. That was done by Alonzo Church 6 months earlier. But Turing gets all the credit because Turing is the one who realized the true nature of computation, is that it's algorithms manipulating symbols. And that gets back to Knut's comment that all of computer science is the study of algorithms. And that's what Turing initiated in his discussion. So that was my missing slides, if you like.
So great to be able to see still the missing slides, and it was a very interesting story still to be told, and I'm happy that we still had the time for this.
Okay. More questions, please. While we're waiting, I can make a remark about Randy. The friendship of Randy and Gardner can't be overemphasized. They spoke on the phone at least once a week their entire life. They were sort of really like brothers. And Randy did lots of things for Gardner. For example, and sounds minor, but it shows the example of how close they were. Randy bought all of Gardner's stationery. You know, he just said, you know, you're a friend of mine, you know, you have bad stationery, I'll supply you with good stationery, and so on and so forth. So they had a very strong relationship to the extent that Randy felt obliged, even though it was not necessary, to help take care of Gardner through his life, just because what else could he do with such a good friend? And of course, also people know that Gardner's famous writing desk is in the possession of James Randi, so that he could look at it every day and be reminded of Martin Gardner.
Well, just prior to the session, CoM was telling also about this story that about the writing desk, and yeah, it's.
I covet the writing desk. I'm going to go after his son, who's going to re-inherit it, and see if I can keep it in my house for a couple months, just so I can look at it. So people who don't know, the writing desk was kept on a stand so that he could stand and work. He sort of was a pioneer in the notion of standing desks, and so that he could get out of his chair every day, because, you know, he sat at a typewriter all day long, so he would have his standing desk, and so people fondly remember him standing at this desk that we keep talking about.
And so you're still writing the biography of Martin Gardner, and you were telling us previously about reaching out to Randy, and
yeah, Randy, when I met him I met him several times, but when I met him at the amazing meeting where CoM and I gave talks about Gardner's life, he has told me that I could come down and visit him and he would answer all my questions about Gardner, and then it never happened. And so that's a great regret of mine, that I never got to have the ability to debrief him on Gardner stories, because I'm sure he had hundreds of them. I'm aware of many of them, but they are old friends going back to the 50s, I believe.
A question back to your talk. Someone asked in the Q&A section in regards to Sam Lloyd's puzzles. So Sam Lloyd's puzzle seems to be asking not for a subset with some 100, but a subset with multiples. Example.
Right. I did acknowledge that it's not the same problem exactly. You would have to have a multiset S to make it the same problem. All right. So in order for it to be the same problem, it has to be multi-set, but that doesn't change the computational complexity of the problem.
So and the question is exactly that. So it's still NP complete.
It's still NP complete, right?
Right.
I see Stan Isaacs asked when the Gardner bio might be published. Well, all I can say is I've been promising it for a while, and I hope to take full advantage of the COVID crisis to find even more time to make even more progress. All right. It's quite embarrassing how long I've been working on this, but I do have a great deal of information. I have, the good news is I have come to the point where I no longer am using the excuse that I'm waiting for more information. I now believe that I have everything, because it used to be I was always finding something new, and why write the biography as long as I'm finding some new stuff? But I think that it's slowed down to a trickle, and I think I can't use that excuse anymore. I do want to point out that I have a bibliography of everything that Gardner has written that extends to 320 pages. So I do have knowledge of and copies of everything he's written, which is of course a great boon, but it also makes the overall task more difficult because he was prolific.
There is one more question regarding the bibliography. Where is it available?
It's not online because I'm trying to get it published.
So I'm sorry for asking all these questions, but something's wrong with my chat things. So when I type, all I get is error messages. So have you tried standing up as you write this book?
Excellent suggestion. That's one of the best suggestions I've gotten in a long time.
So with this, I think we have reached our full time. Thank you so much, Dana, for this amazing talk. And I think we can stand up and start working on other things. I shall. So thank you, everyone, all attendees who have joined. Thank you very much, Dana.
Bye-bye.